Today we're going to be looking at matrices, row echelon form, and reduced row echelon form. Please be sure to subscribe so you don't miss out on any future videos. A system of linear equations can be solved by using matrix algebra. A matrix is a rectangular array of numbers arranged in rows and columns. Here is an example of an augmented matrix for this system of linear equations. The number of rows in a matrix is the number of equations. Since there are 3 equations in this system, we have 3 rows. The number of columns in a matrix is the number of variables plus 1. Since we have 3 variables, x, y, and z, there's 3 columns plus 1, so a total of 4 columns in this matrix. The first 3 columns represent the coefficients of the variables, and the 4th column represents the constant terms. A matrix written without the constant term column is known as a coefficient matrix. Next, let's look at an example. Let's see how equation 1 is written in the augmented matrix. Since this is equation 1, all the coefficients are going to be written in row 1 and under their corresponding variables. Variable x has a coefficient of 2, therefore we've written 2 in row 1 and under x, the variable x. There is no variable y in this equation, therefore a coefficient of 0 is written. There is a coefficient of 2 written in front of the variable z, therefore we have a 2 in column z, row 1, and a constant term of 4. A similar approach is used to populate rows 2 and 3. This augmented matrix is important because in the future we will use this matrix and transform it into row echelon form and reduced row echelon form to solve the system of linear equations. A matrix is in row echelon form if it satisfies the following 2 properties. Rows containing only zeros are at the bottom, and the first non-zero element of any row is the leading entry and is to the right of the leading entry in the previous row. Let's look at some examples. For this first matrix here, we have a row that consists of only zeros and it's at the bottom. Therefore, it satisfies the first condition. The first non-zero element in row 1 and 2 are circled in red. The leading entry in row 2 is to the right of the leading entry in the previous row, which is row 1. Therefore, it satisfies this condition, and this matrix is in row echelon form. Let's look at another example. There are no rows consisting of only zeros, therefore we don't need to worry about this first condition. But now let's look at the second condition. We can see that the leading entry for row 1 is this coefficient 1 here, and the leading entry for row 2 is this 3. This leading entry is to the right of the leading entry in the previous row, therefore it satisfies the second condition. However, the leading entry for row 3 is to the left of the previous leading entry, therefore this condition is not satisfied and this matrix is not in row echelon form. Let's look at one last example. The leading entries here, 1 and 1 here, this leading entry is to the right of the leading entry in the previous row, therefore this matrix is in row echelon form. Next, we will look at reduced row echelon form. A matrix is in reduced row echelon form if it satisfies the following 3 properties. First, the matrix must be in row echelon form, which we've just discussed earlier. Second, the leading entry in each non-zero row must be a 1, and all elements above and below the leading entry are 0. Here is the notation for a matrix in reduced row echelon form. We can see that the leading entry in each non-zero row is a 1, and all elements above and below the leading entry are 0. Therefore, this matrix is in reduced row echelon form. Thank you for watching. Please like, share, and subscribe.